Hi, my name is Chen Wang. Today, I'm presenting to you our recent work, Six-Pack, which is a category-level 60-object pose tracker with anchor-based key points. Estimating 60 poses of objects, which consist of translation and orientation in 3D, offers a concise and informative form of state representation for robotic applications, such as manipulation and navigation. Commonly, there are two ways to acquire the 60-object pose. For estimation method, the model takes each frame as input and directly output the pose projection of the object in this frame. For tracking methods, as is shown in the bottom right video, given the object pose in the first frame, the model consistently estimates the object pose changes between two consecutive frames and tracks the object over time. In robotic applications, tracking is more commonly used because it makes use of the temporal consistency and object permanence to make the estimation more stable. However, one of the major challenges of tracking objects in daily life is their diversity in geometry and color. Having a complete and accurate model of each object we want to track is a strong assumption in many domains, like robots in homes or logistics centers. This finding arouses the question that how to track the pose of these unseen objects. Is it possible to track their pose without knowing the 3D mesh model? To tackle this problem, we need to move away from estimating pose based on the entire object shape, because that changes between instances. 3D key points are more local and should be able to retain better category-level regularities. For example, the handle of the mug in these images contains rich information for pose estimation, and is a typical characteristic for this mug category. Historically, 60-object pose estimation has relied on solving an error minimization problem on the matching between the current view to a given template object model. However, as is mentioned previously, these methods are based on the assumption that the object model is none, which fails to generalize to real-world tracking for unseen objects. Our method tracks unseen objects within the training category and does not require the object model. Recent learning-based methods achieve more robust performance against occlusion and illumination changes. Also, after training the model with a large number of different objects from the same category, the learned model shows ability to estimate the pose of unseen objects without knowing their mesh models. Knox by Wang et al. And our method both achieved this category-level object pose estimation capability, but our method is focused on tracking and improves the result by exploiting the temporal consistency and category-level object key points generation. In this work, we introduced an anchor-based key point generation method to tackle category-level object pose estimation in a tracking fashion. The model takes RGBD inputs from the robot camera as input and generates a set of 3D key points. The pose changes between two consecutive frames are calculated based on the generated key points from the two frames with a differentiable least squares optimization. The object pose at the current time step is calculated by accumulating each interframe pose changes along with the given first frame pose. While the feature-based pose tracking procedure is similar to previous methods, our novelty lies in the way we generate key points, learn from data, and based on a recursive anchor mechanism which I will explain in the following. The main component of Six-Pack is the anchor-based key point tracking model, which is trained unsupervisedly and achieves real-time inference speed for category-level 60-object pose tracking. Here I will introduce the pipeline of the tracking process. Assume the object pose and moving direction on the previous frame is already acquired. The model first uniformly samples a grid of 3D anchors around the centroid of the previous pose. When it comes to the current frame, a temporal translation is applied to the generated anchor grid. Then, an attention network selects the anchor that is closest to the centroid of the object in the current frame. After that, a set of 3D key points are generated as offset points from the selected anchor. The pose changes between the current and the previous frame are then calculated through a differentiable least squares optimization. Finally, the estimated interframe pose changes are applied to the anchors and get ready for the tracking in the next frame. Here we illustrate the details of the anchor-based keypoint network. We use dense fusion as our per-point level feature extraction network. In our previous work, dense fusion has been proven to be successful for pose estimation because of its capability to generate features that include rich information from both color and geometry modalities. Then, after uniformly sampled 3D anchors, each anchor generates their own feature with a distance-weighted average pooling among all the feature points. After that, an attention network predicts the anchor that is closest to the centroid of the object. Based on the selected anchor, a keypoint network generates a set of offset points from the anchor. The unsupervised training of the keypoint network contains two main objectives: an anchor attention loss, where the confidence score of the anchor that closest to the object centroid need to be the highest. A pose estimation loss, where the interframe pose changes acquired from the differentiable least square optimization need to close to the ground truth. We also include several losses to maintain some basic characteristics of the generated 3D keypoints, such as the multi-view consistency and point separation. We evaluate our model on the Knox real dataset, where 6-pack achieved the best performance among all the baselines. Here is a qualitative comparison between Knox and 6-pack. All the objects have not been seen during training, and their mesh model are also not given. From these videos, we can find that Knox often lose estimation result in certain frames. This is mainly because as a typical pose estimation method, Knox heavily relies on their object detection ability. When the detection fails in some frames, the pose estimation process will also be blocked. For 6-pack, by using the anchor-based mechanism to enforce the temporal consistency between frames, our method performs more stable and accurate in tracking the object pose. In the last video, even with abrupt camera motions, 6-pack does not lose track of the object. Here is a qualitative result of the keypoint generation on the testing unseen object set. As we can see in the left figure, the white ball and mug are textureless objects, which are difficult for classical salient detection method to find the keypoints. Since 6-pack generates a set of keypoints in one forward loop, some keypoints that are difficult to discover could be roughly inferred by other keypoints which are more salient in geometry or color. In the right figure, we visualize the keypoints of the 3 unseen laptops in similar object pose. We can clearly see the correspondence between these 3 sets of keypoints on different objects. We apply 6-pack onto a real robot platform. Our method achieves 10 frames per second tracking inference speed with an NVIDIA 1070 GPU. All the objects here are unseen objects. The green bounding box is estimated 60 pose of the object. In this experiment, a student is holding an unseen ball object in front of the robot. The robot keeps tracking the object pose and moving its head towards the target object. Note that moving the head introduces a quick motion, but our tracker does not lose track. Then, the robot is given a bottle and trying to pour the particles inside the bottle into the ball. To accomplish this task, the robot needs to accurately and consistently track the pose of this object. Our method successfully tracks without loss the object in more than 60% of the trials. We presented 6-pack, an unsupervised 3D keypoint generation framework for category level 60 object pose tracking. Our code is also available. Thanks for watching.